Okay, so the the next ones here, we got a couple of these so-called measures of position. They tell me about a value position-wise where that value is in the values overall. That's what we're going for here. One of them is what's known as a z-score. Z-score, that gives me a score for a particular value. And what it is, the z-score, it's the number of standard deviations a value is from the mean. So it's not just the deviations from the mean, which we talked about just a second ago. It's the number of standard deviations from the mean. Okay, and so if we have some easy ones, we can do those pretty. So let's say we've got a distribution has mean, let's say 45, and then standard deviation is 3. So if our value, so the value of, from the distribution of 48, that has a z-score of 1. The value 48 for this particular example would have a z-score of 1 because notice, means 45, and so 48 is one standard deviation, right? If I add one standard deviation to 45, I've got 48. So that means that 48 has a z-score of 1. Which value would have a z-score of 2? Which value would have a z-score of 2? Well, if I add 2 standard deviations to 45, what does that give me? 51? 45 plus 2 standard deviations, 3, and then another 3, that's 51. Okay, so you get the idea. It's how many standard deviations. It's not how far away from the just subtracting the mean. Here you're talking about z-scores. That's what the z-score is. Okay. Now, if you go below the mean, like if I went to 42, 42 would have a z-score of -1. Right? Because it's one standard deviation away, but it's below the mean. Right? Subtract 3, you got 42. So that's a z-score of -1. So if you have a z-score that's negative, that just means it's below the mean. Okay. Now, that's whole number z-scores, but z-scores can be decimal values too. Here's the formula for z-score. What you do is you take the value minus the mean and then divide by the standard deviation. That's how you compute z-score. Now you might notice there, value minus mean, that's deviation, and so you divide by the standard deviation, so that's what's kind of different about the z-score. You're dividing by the standard deviation. Okay, so back to our example here then. What would be the z-score of, let's just make it 50. So we've got a mean of 45, standard deviation is 3. What's the z-score of 50? Well, the z-score of 50, let's write it this way. Yeah, that's not a nice number of standard deviations because it's 5 units, but just use this. So value, so you take the value, 50, minus the mean, which is 45, and then divide by 3. So it's 5 divided by 3, and usually it's a decimal. They put it in decimal form. 5 divided by 3 is 2.6, and then let's say standard operation here, we'll go with 2 decimal places. 2.67, 5 divided by 3. So that would be the z-score of 50. Okay, so it's just a little bit of calculation there. What about the z-score of, let's just do 40. For this particular scenario here, what's a z-score of 40? Well, the z-score of 40, you take 40 minus the mean divided by the standard deviation, you get negative 5 divided by 3, so you get a negative 2.67 there.
Is it not 1.67?
Oh, 1.67.
Sorry.
Just checking. 1.67, thank you. And negative 1.67. Okay. All right, so this is a pretty easy calculation. You just have to know this little formula here. Now, one thing that this does is this standardizes this position. So, you know, like we said, if we've got a negative z-score, we know it's below the mean. If it's a positive z-score, it's got to be above the mean. But it also allows us to compare scores from different distributions. If we have a, you know, if we have a score from 2 different distributions, and we want to say, well, which one's better, you know, relative to the other values in the distribution. This z-score gives us a way to do that because it kind of standardizes, you know, 1.67 standard deviations in this distribution is similar to another distribution if you have a z-score of 1.67. If we're just talking about deviations, well, you know, that, so it kind of standardizes things a little bit. And so that's what we're going to do here next is compare values from 2 different distributions. And we're going to use this z-score. Okay, so let's say we got Matt. And he made, Matt made a 75 on his history test. Joyce made 60 on her science test. So they got to comparing here. And looks like Matt made a higher score, but did he really make higher? So here's what else we know. All right, so the mean from the history test, it turned out to be 68. With a standard deviation 2.3. The mean on the science test, though, was 52. With standard deviation 1.9. That's my symbol for width there. All right. So, relatively speaking, to the other people in the class, who in those classes relatively speaking to others in each class, who did better on their test? Well, at first glance, again, maybe it looks like Matt, but the mean, the average on his test was 68, and the average on the science test was 52. So, you know, there's different things going on. It was looks like it was a harder test, if we're talking about out of 100, looks like it was a harder test on the science test, so maybe Joyce did better. So how do we, and that's what we're going to use here is the z-score, because the z-score standardizes this positioning of the values. Okay, that's what z-score, one of the things z-scores, we'll use it for other things, but the z-score kind of standardizes the positioning of the values amongst different distributions, okay? So we're going to use z-scores. So let's do Matt's z-score and Joyce's z-score here. All right. So z-score for Matt. So the z-score, you take the value minus the mean, divided by the standard deviation. So his score was 75. The mean for the history test, what was it, 68. Divide that by, standard deviation was 2.3. So we got 7 divided by 2.3. I see that as being 3.04. Okay, what about Joyce? Well, Joyce's value was 60. The mean was 52, and then the standard deviation was 1.9. So that's 8 divided by 1.9. That is over 4. Know that. It's 4.21. So again, knowing, you got to know what this z-score represents. The z-score, that's the number of standard deviations from the mean. That's what the z-score represents, the number of standard deviations from the mean. So, you know, the more standard deviations are from the mean, the better your score as far as the test goes. You know, the further out, you're further out from the mean, so you've done better on the test, so to speak, in this particular case you're talking. So, Joyce did better, didn't she? The higher z-score, in this case, wins. Joyce is further out from the mean as far as standardized deviations, standard deviations. That's what the whole goal of this was. All right? Joyce did better. She's further out from that mean standard deviation line. So Joyce's would be better. Any questions about that? All right.